Infinity is a concept that might seem simple, just the absence of limits. Yet, the closer we look, the more it seems to retreat from our understanding. Does infinity come in different sizes? Could an infinite hotel be fully booked and yet still have room for more guests? And what happens when even mathematics can't keep up? In this place, which Cantor calls the absolute infinite, would we find God if only we could reach it? Who better to pick through these topics than Adrian Moore, Professor of Philosophy at the University of Oxford? He's thought deeply about how the infinite connects with mathematics, metaphysics, and even theology. He's written many excellent books. Most relevant to today's discussion is The Infinite, where he chronicles the thousands of years of history where humans have grappled with this concept. Today, we discuss Cantor's hierarchy of infinities, Hilbert's paradoxical hotel, and whether the infinite is something that we can ever truly comprehend. Beyond the maths and the philosophy, this is a story of human curiosity. What is it that draws us, finite beings, to this idea so vast, so unknowable, yet so irresistible? I'm James Robinson, and this is Multiverses. Hi, Adrian Moore. Thank you so much for joining me on Multiverses.
Thank you very much for the invitation, James. It's a pleasure to join you.
So I think the infinite is something that children start to think about fairly early on. In my experience of having a 7-year-old boy, he's already noticed that there's bigger and bigger numbers, and he asks, well, is there a final number? And there is none. So that's kind of maybe one route which I think in childhood we first encounter the infinite. Another perhaps quite different route is we might look out at some unbounded ocean or the stars above and start to think, well, here is some great majestic thing that's beyond my comprehension, and we might think of that as the infinite as well. But these are two very different routes. Are they really pointing towards the same thing? Is there something even there that they point to?
So I think that's a really interesting question to start with. And if I may, before I go any further, if I may preface my remarks with a reference back to your 7-year-old son. There's no doubt that infinity is a concept that even young children latch onto at quite an early stage and are exercised by and are fascinated by. And it's also a topic which has always been of interest to philosophers. I mean, if you go right back to the ancient Greeks, it was one of the concepts that they wrestled with. And I'm flagging this because it reminds me of something that I very often say to people when they ask me what philosophy is or what a philosopher is. And one of my favorite answers to that question is a philosopher is somebody who's never really grown up. I mean, I think what we do a lot of the time is ask the questions that children ask. I mean, the fact that children notoriously are asking why all the time, which is something, of course, that philosophers do as well. And the fact that children do think about the infinite and are soon exercised by the fact that there's no biggest number or wonder whether there's anything outside space. And it is striking that this is a concept that grabs our attention at such an early stage. But the question that you've raised is whether we should even really be talking about a concept or whether there's perhaps more than one concept. You mentioned the fact that your 7-year-old son has already noticed that numbers go on indefinitely, that there's no biggest number. but you also talked about the kind of experience that we have when we look out at the horizon or look up at the night sky and see all those stars shining and wonder whether space goes on forever. And there's perhaps a third route in that you might have mentioned as well, which is something else that small children think about, which is, is there a God? And if there is God in some way infinite? And does that have anything to do with the fact that numbers go on forever? Um, my own view is that there are clusters of concepts here. I think perhaps we shouldn't be thinking of the infinite as a single concept. Um, there's a lot of interrelated ideas that are going on here, and sometimes interrelated in quite unexpected ways. And one of the issues is how they're related, what the character of the interrelations are, how these different concepts hook up with one another, and why it is that we use the same word in connection with all of them. Um, and unfortunately, I don't have anything very pithy to say in response to that. I mean, it's not because, if I may blame my own trumpet, it's not because I have nothing to say in response to that. It's almost the opposite problem. There's too much to be said. I mean, there's a lot going on here, obviously, but one thing that I think is very striking, and maybe we'll get on to a discussion of this in due course, um, is that some of the very, very technical mathematical work that's done on the infinite, um, in its own interesting way, turns out to have connections with some of these more mystical aspects of the concept. Um, and as I say, maybe we'll get on to a discussion of that in due course. But I'm flagging it at an early stage. And in particular, the other thing that I'd like to flag at an early stage is that we find this especially in the work of the great German mathematician Georg Cantor. Um, Cantor was a 19th century mathematician, brilliant mathematician who did outstanding work, um, and is generally reckoned to be the father of what's often called transfinite mathematics, formal mathematical work on the infinite. Um, and he was also somebody who was deeply religious. He had quite a profound belief in God as well. Um, and he himself thought that there were interesting and deep connections between the mathematical work that he was doing and some of his own religious convictions. And we can explore that if you want to. But as I say, I thought it was perhaps going to be helpful to flag at an early stage how even the most technical work on the mathematical infinite has a bearing on these more mystical or theological or metaphysical conceptions of the infinite.
Yeah, yeah, I definitely want to get to that. So I think another, it just struck me as you were speaking that perhaps another way these quite disparate ideas maybe intersect, or maybe it's better put that they have something in common, which is that with all of them, there are paradoxes that you can find with the idea of God. Can God make something so big he couldn't move it? Or with space and time, of course, there's the paradoxes that Zeno proposed or wrote about in ancient Greece. Achilles and the tortoise. Perhaps we could go into that, and then of course Cantor's formal mathematical work. It's, I mean, I would say that it creates paradoxes to me. Perhaps to a mathematician, they're like, no, this is all very straightforward, but it does have very counterintuitive results, which I would say are quite paradoxical to my understanding.
Yeah. Well, that's certainly true. Whether you think that these paradoxes are ultimately troubling or not, whether you think that they point to some profound contradiction that we just can't get our minds around, or whether you think that they're nothing more than results that are counterintuitive. Whatever your stance, they're at least paradoxical to that extent. I mean, some of the formal results are at the very least counterintuitive, and some of the puzzling features of divine infinitude, if you are somebody that believes in God, again, at the very least, are counterintuitive. Some people think it's worse than that. Some people think that there's something fundamentally contradictory involved in the very notion of the infinite, and that either this goes to show that we really just can't make sense of the infinite, or it goes to show that our talk of the infinite is a way of gesturing at something that can't properly be expressed, or something along those lines. And one of the things that anybody has to do who's trying to come to terms with the infinite and trying to make sense of the infinite is they have to decide what to do about these paradoxes, what the appropriate reaction is. Again, I'm very much in your hands whether you think it's worth discussing particular paradoxes to see what we might make of them. I'd be happy to do that, and as you indicated earlier, there are plenty of them to choose from.
Yeah, I
I mean,
wonder if do you have any favorite ones that you think really, I don't know, cut to the heart of the matter? Or
well, maybe we could talk about Hilbert's Hotel. Are you
yeah,
familiar with Hilbert's Hotel?
I'd love to visit.
Okay, I mean, but some of your viewers may not be familiar with Hilbert's Hotel, so let me see if I can introduce this paradox, family of paradoxes, actually. So before we go any further, we need to talk about something that lies at the very heart of contemporary formal mathematical work on the infinite, and that's the very idea of what it is for two sets or two collections to be the same size as each other. Sometimes you can tell that two sets are the same size as each other just by counting. So let's suppose that you're in a room at a meeting, and for one reason or another, your mind is wandering, and you're just wondering whether the number of men in the room is the same as the number of women. And you look around you, and you can quite quickly settle that question simply by counting. And it may be that you count the number of men and you see that there are 12 men in the room. And then you count the number of women and you see that there are 12 women in the room. And you conclude that these two sets are the same size as each other. The set of men in the room and the set of women in the room are the same size because there are 12 of each. And that's very straightforward and very familiar. And again, this is an operation that very small children are accomplished at performing. But sometimes the question arises whether two sets are the same size as each other, and you can't resolve it by counting. but nevertheless you can resolve it. And a simple example of what I have in mind is, suppose the question arises, is the number of firstborn twins that are alive? Let's suppose we confine our attention to twins where both twins are still living. Is the number of firstborn twins that are still alive the same as the number of second-born twins that are still alive? And I think neither you nor I know exactly what either of those numbers are. I mean, I'm sure nobody knows what either of those numbers are. We might be able to make an estimate, but it would only be an estimate. Nevertheless, we can answer the question whether those two sets are the same size. We can see that they are. There must be just as many firstborn twins as second-born twins. And the reason that we can answer the question, even though we're not in a position to count the two sets, is that we can see that the members of the sets can be paired off with each other. To each firstborn twin, there corresponds a second-born twin, a unique second-born twin, and vice versa. To each second-born twin, there corresponds a unique firstborn twin, and vice versa. They can be paired off with each other, and so we're in a position to conclude that those two sets are the same size, irrespective of how many there are. We don't need to go out and count. Now, so far so good. But the sets that we've been thinking about so far, the number of men in the room, the number of firstborn twins, are finite sets. But paradoxes begin to arise if we turn our attention to infinite sets. So, we've claimed that if you can pair off all the members of one set with all the members of another, then we have to conclude that they're the same size. Well, now think about the set of natural numbers, 0, 1, 2, 3, 4, etc. And think about those that are even, 0, 2, 4, 6, 8, etc. Well, obviously, these can be paired off. To each natural number, there corresponds a unique even number. It's double. And to each even number, there corresponds a unique natural number. It's half. And so it looks as if we're obliged to say that there are just as many even numbers as there are natural numbers altogether. And yet there's a very strong intuition tugging in the opposite direction, that no, surely there are more natural numbers than even numbers, because the natural numbers include all the even numbers, but they also include all the odd numbers as well. So that's already paradoxical in as much as, at the very least, it's counterintuitive. I mean, there are now questions that remain to be addressed about what we should say, what's the best way to describe what's going on here, do we have to say there are just as many even numbers as natural numbers? Are there reasons for resisting saying that, etc., etc.? But now let me turn my attention to what's called Hilbert's Hotel, which is a variation on the same theme, where the paradoxical nature of this result really kicks in. So Hilbert's Hotel is a hotel named after the 19th, 20th century mathematician David Hilbert, who used to discuss it in lectures that he gave on these topics. And he asked you to imagine a hotel that has infinitely many rooms. And he also asked his audience to imagine that at a particular point in time, every single room is occupied. They're full. And a stranger turns up late at night, and it's a cold, wet, miserable night. It's raining heavily, and he would love shelter for the night, and there's no other hotel nearby. And he asks whether he can be accommodated in the hotel for the night. And the receptionist says, well, I'm sorry, we're absolutely full. And the guy says, but am I not right in thinking that this is a hotel with infinitely many rooms? And the reception says, well, no, you're right. You are right in thinking that. And the stranger says, well, then you can accommodate me. All you need to do, as long as the other occupants are amenable to this, all you need to do is to ask the person in room 1 to move into room 2, the person in room 2 to move into room 3, the person in room 3 to move into room 4, etc. They'll all be accommodated. Nobody will miss out because there are infinitely many rooms available. And that will free up room 1, says the stranger. And I can move into room 1. And the receptionist says, well, what a brilliant idea. Let's do that. But then the next thing they know, infinitely many people turn up wanting to be accommodated. And again, they're met with the same response. Well, I'm sorry, we're now fully occupied. And again, they tried this ingenious move, reminiscent of the discussion that we were just having. And they say, well, no, you can accommodate all of us. Ask the person who's currently in room 1 to move into room 2. Ask the person who's currently in room 2 to move into room 4. Ask the person who's currently in room 3 to move into room 6, etc., etc. They'll all have a room to move into. That's no problem. And by the time you've done all of that, the infinitely many odd-numbered rooms will be available, and these infinitely many people that have shown up can all be accommodated. And as I say, that's paradoxical, at least to the extent that it's counterintuitive. Whether it's any worse than counterintuitive is a further question. But at the very least, there's something a little puzzling and rather shocking about the situation as I've just described it.
Yeah, and it's very hard. Sort of going from a physics background, it's kind of hard to test these things, right? I mean, it's a concept, so I mean, it must be true. I mean, it's just based on the mathematics. There doesn't seem to be anything wrong. But it is one of those things that we kind of like to see it happen.
Yeah. Well, I mean, that's an absolutely fair point that you're making. I mean, this is a purely conceptual exercise. And when we're imagining an infinite hotel like this, it very much is an exercise of conceptual imagination. There's no way that an actual physical hotel could be infinite. I mean, you might try to envisage even a physical hotel with infinitely many rooms by envisaging the rooms getting smaller and smaller. So each room is sort of half the size of the one next to it, and you can sort of squeeze them all in that way. But I mean, you know better than I do. You're a physicist, and I'm not. But I'm sure that even that isn't going to make ultimate physical sense. There are going to be problems about what's going on at the very small level, and physicists, as you know better than I do, tend to recoil the minute they encounter the infinite. But mathematicians and philosophers are are more likely to feel at home in this more conceptual territory, I think. And what a lot of mathematicians would say, and for that matter, what a lot of philosophers would say, is that even if it's physically absurd, or even if it doesn't make any physical sense, Hilbert's hotel makes perfectly good conceptual sense, um, and all it is counterintuitive. Um, the idea that a hotel could be full at a given time and still have the resources to accommodate a newcomer without anybody having to move out. Well, puzzling, yes. Logically contradictory, no. Makes perfectly good sense. And that is, as I say, that's the reaction that uh, many philosophers, many mathematicians have to this kind of paradox.
I do want to get back to the points about physics, but I think first, now might be a good time to talk about one of Cantor's great contributions, because I think you've lined it up very well in terms of saying, okay, well, look, actually, the maths shows us that the size of the set of even numbers is the same as the size of the set of all the real numbers, and that seems odd because one seems to fit within the other, and it might be natural for people to be thinking, okay, well, it just turns out that all infinities are the same size, and once we get to that number, it's just one thing, and it's weird. But it turns out it gets even weirder than that, at least in my mind. And I
Yeah.
think it's just a wonderful, a brilliant example of Cantor's genius, how he proved that. So
Yeah, well, let's use this as a cue to start talking about Cantor then. I mean, as I've already mentioned, he was a brilliant 19th century mathematician who was the first person who did really serious, rigorous, formal work on the infinite. And precisely what he was doing was capitalizing on this idea that we've been toying with, of what's involved in two sets being the same size. And as you quite rightly point out, if all we had was the example of the even numbers, then you've got these puzzling results like Hilbert's hotel, but nevertheless, there would be scope for the view that it's actually ultimately not that counterintuitive. Because you might think, okay, so what this goes to show is that we can distinguish between various different finite sizes. We might be in a position to say that the number of men in the room is greater than the number of women because there are 13 men and only 12 women. And so there's an example of one set that's bigger than another. So you've got these various different finite sizes that sets can be, and then you've got the infinite. And if it turned out that all infinite sets were the same size, you might take the view that actually that's not particularly counterintuitive, that in fact that's intuitive. That's in a way what you might have expected, that once you get into the realms of the infinite, it's no longer possible or appropriate to start trying to distinguish between different sizes. That's what you might think. And that's exactly what Cantor showed to be incorrect. And this is, one of the most striking and most remarkable features of his work. Cantor showed that there are cases where you've got two sets and it's not possible to pair off all the members of one of them with all the members of the other. And what you have to conclude is that one of these infinite sets is bigger than the other. They're both infinite, but one of them is infinite, as it were, to a greater degree than the other. And Cantor showed that can happen. Now, I don't think, unfortunately, that it's possible for us to go over the proof in this context. Apart from anything else, it's best done visually. And some of your viewers will already be familiar with this result, and I'm hoping that the viewers that are not familiar with it will take our word for it, at least for the time being. And then there are places where they can look it up if they are interested. But this is what Cantor showed, that some infinite sets are bigger than others. Yeah. But actually, that's not the end of it, because he also showed, given any infinite set, there always will be another that's bigger than it. In particular, I mean, we were talking earlier about the set of natural numbers, and he showed that the set of sets of natural numbers has more members than the set of natural numbers. So if you start off with a set like the set of natural numbers and then consider the set of all its subsets, that will always give you a bigger set than you started off with. But then you can consider the set of sets of sets of natural numbers. You can consider all the subsets of that new set, and that will be even bigger. And then you can consider the set of sets of sets of sets of natural numbers, and that's even bigger. And so what Cantor was forced to conclude was that not only are there different infinite sizes, there are infinitely many different infinite sizes, that these orders of infinity get bigger and bigger and bigger without end. And that's really what gives his work a lot of its interest, because what he then did was started to explore the ways in which you can do proper formal mathematics with these different infinite sizes. You can assign measures to them just as we assign measures to different finite sizes. And that means that there are infinite numbers, and you can add these numbers and you can multiply them. There's a whole branch of mathematics here which is known as transfinite arithmetic, and it has fascinating results. And that was what Cantor established, a whole branch of mathematics, basically.
Yeah, so I think if people want to look up the proof, if they search for the diagonal proof or diagonal argument of Cantor, as you said, it's a very visual proof. But I think the other way of kind of getting to the result is, like you say, thinking about the sets of sets, or the different. Once you have a set of numbers, the power set of that, which is all the different ways that you can arrange its members into different sets, that gets you to a bigger infinity. And then when you're at that bigger infinity, you can do the same thing again. You can say, I'm going to take the power set of this infinity, and that gets you up the other level. Actually, my mind's going back to sort of, again, I'm very full of childhood analogies at the moment, probably because I have a young son. But if you're in the playground and someone says, "Oh, you're it times 10," and then you take them back and you say, "You're it times infinity," and then they say, "Oh, well, you're it times infinity plus 1." I mean, the real response should be, actually power set of infinity of the countable numbers or something. So there is actually a valid response there. If there's any young children listening to this, they can get one up on their friends by using something like that.
Yeah, but again, I'm totally with you. I mean, I think there's something very sort of childlike about this fascination that we have with these results, and there's something childlike about the way in which they pan out. Just when you thought it couldn't get any bigger, there's a way of making it even bigger. But I wonder if perhaps I can now use this as an excuse to talk about the thing that I mentioned much earlier, which was how Cantor himself thought that this related to some of his religious beliefs. Because he was religious and he did believe in God, and he believed that God had a kind of infinitude. And he also took it that some of his formal work on the infinite was, in its own way, a kind of vindication of talking in such terms, being prepared to talk about an infinite being. But the connection was not as straightforward as that. And if I can, I'll try and explain why it was unstraightforward. So let's go back to the point that you just made, that one of the things that's going on here is that we have to appreciate that any set is smaller than its own power set. So the set of natural numbers is smaller than its power set. The power set of the natural numbers is smaller than the power set of the power set of the natural numbers, and so on indefinitely. And this is why we have to acknowledge bigger and bigger orders of infinity. But supposing somebody comes along and says, well, hold on a sec. What about the set of all sets? Supposing you sort of throw a big lasso around all of them, how can that be smaller than its own power set? Because its power set is just another set of sets. But what we started off with was the set of all sets. So we've already included all of those. So something's gone badly wrong here. And Cantor was well aware of this puzzle. And by the way, I mean, some of your viewers, most of your viewers, I'm sure, will have heard of something called Russell's paradox. And basically, we're skirting Russell's paradox. I mean, we can talk a little bit more about the connection if you want to, but suffice to say that this question, what about the set of all sets, is in effect a variation on Russell's paradox. But anyway, what about the set of all sets? I mean, let's go back to that question. And Cantor was well aware of this question, and was well aware that it was, there was something threatening about it. It seemed to undermine all that he'd been doing. But actually, and this is part of Cantor's genius, this is part of the reason that he's such a brilliant mathematician. He refused to be fazed by it. He didn't let it undermine all his work. What he did was he said, look, you eventually reach collections like the collection of all sets that are so big that they don't have a measure any longer. There's no such thing as an answer to the question, how many sets are there altogether? We've now reached the point that we can't any longer assign a measure. And Cantor, I mean, there are various bits of terminology he used. Sometimes he talked about inconsistent totalities. But another bit of terminology that he used in this connection was he sometimes talked about the absolute infinite. And what he was doing was gesturing at this kind of infinity that escaped even his own formal technical apparatus. And this was the connection that he saw between his mathematical work and his theological beliefs, because he thought that the kind of infinity that God enjoys, the kind of infinitude that we have to ascribe to God, is of this more radical kind, the absolute infinite, the sort of infinite that's beyond measure. So when he said that he believed God to be infinite, and when he was doing formal work on infinite collections, those two kinds of infinity were not directly related. They were indirectly related through this connection with the absolute infinite.
Right. Yeah. Let me try to read that back because I think it's a really
Okay,
powerful.
good. Because I'm never very sure how much sense this makes when people are encountering it for the first time. So, yeah.
I think it's just a very powerful idea, and it probably bears repeating. So something like, I mean, we have this very intuitive idea that the power set. I mean, it's clear that the power set is bigger than the set, and that makes perfect sense, right? You take the natural numbers. It's clear that you can create lots and lots of more collections of those. You can put them into more buckets than there are natural numbers. Or maybe that's not clear, but it's certainly provable. But it does feel normal. Certainly, when you start with finite numbers, it's easy to see how that works. There's 3 people in a room. You can put 2 together, or the other 2, or in various different ways, or have them each on their own. So that all well and good, starts very simple. But then you kind of reach this point where your sets are so big and that they seem to suggest that the maths is breaking down. And I guess Cantor's response to this is, well, the maths has reached something that it can't decide, but it's maybe pointing towards a place where math doesn't go, but there's still something there, right?
Yeah.
Because another response would just be, well, there's nothing there, and perhaps that's a legitimate one, but it's hard to see why there wouldn't be anything there, because it's, what's wrong with being able to arrange things into different sets? And you might say, okay, well, it makes sense to arrange the natural numbers into, I can arrange those into different sets, but and what's wrong with arranging the sets of the sets that I've made into different sets? But maybe there is. The other thing I wanted to say, just makes perfect sense, is that it is intuitive that there should be more kind of ways that things could be than there are, and I guess that's loosely linked to this idea that you have a state of affairs, you have a set of things, but you could arrange them conceptually in many more ways than they actually are. I did just want to mention as well that Russell's paradox, in case people aren't aware of it, it's very simple to summarize. It's just the classic statement is, there's this barber on an island, and he's only going to shave. He's going to shave all and only those people who don't shave themselves. And the problem is, well, again, does he shave himself or not? Because if he does shave himself, well, he shouldn't be shaving himself, because he said he's only going to shave the people who doesn't shave themselves. So you get this kind of self-referential problem, which is very analogous, as you say, to the problem of sets. But one doesn't conclude from Russell's paradox, oh, God, right? So on the one hand, there's something very appealing about Cantor's proof, because we've reached this, grandiose state where math seems to be breaking down, and yet we don't know why. On the other hand, maybe there's just like a prosaic explanation, which is, well, don't go there, right?
Yeah.
It broke down much earlier. But where, I don't know.
Yeah. Well, good. So I like the way that you've put this, and I mean, if I can, if uh, grind an axe of my own at this point, again, this is perhaps a nice excuse for me to do so. I mean, my own view, for what it's worth, is that we have to be very, very skeptical about whether we can grasp the infinite, whether we can really properly make sense of the infinite, whether we can tame the infinite. And I think there are all sorts of reasons for denying that we can. Now, often, if you express a view like that, often mathematicians in particular turn round and just present Cantor's work, and they say you're just being absurd. This is mystery mongering for the sake of it. What Cantor did was to show that we can make sense of the infinite. Here's this really rigorous, formal mathematical work that's unassailable, work of the very highest caliber, in which exactly what he's doing is showing how you can measure infinite sets and do calculations with infinite numbers and blah, blah, blah. So what are you talking about, saying that we can't make sense of the infinite? And so my response to that is not to challenge Cantor's work, which is absolutely unassailable, and I agree is work of the very highest caliber. I mean, this is mathematical craftsmanship of the greatest kind. So that's not in dispute. I mean, let's not quarrel with Cantor. You need to be a very foolhardy kind of philosopher to think that you could quarrel with Cantor. That's not the issue. The issue is what we mean by the infinite. I mean, this takes us right back to square one. I mean, the opening question that you put to me, what is our idea of the infinite? And if you ask most people what they understand by the infinite, you're going to get a variety of different responses. But I think there's a very, very good chance that it's only a question of time before concepts like endlessness, unlimitedness, and immeasurability get a mention. At some point, somebody is likely to appeal to one or more of those concepts. If they're more theologically minded, perhaps they'll start talking about perfection or omnipotence or something like that. But certainly if it's somebody that's more mathematically minded, as I say, there's a good chance they'll talk about what goes on forever, what's endless, what's unlimited, what's immeasurable. And indeed, those are the sorts of words that you're liable to find in a dictionary if you look up the infinite in a dictionary. So let's go back to Cantor's work. Where do those concepts apply? They apply to the whole hierarchy. It's not true that the set of natural numbers exhibits endlessness or unlimitedness or immeasurability. Because what Cantor does is show that we can measure it. He gives a precise numerical definition to how big it is. And you don't have proper endlessness there because the argument that you sketched earlier about each set being smaller than its own power set, the endlessness is emerging further up the hierarchy. I mean, the endlessness is the endlessness that you get as you travel higher and higher and higher up this hierarchy of power sets. And it's not unlimited either. It's limited in size. That's precisely the point. There are fewer natural numbers than there are sets of natural numbers. The really unlimited, the really immeasurable, the really endless looks as if it's what emerges when we're dealing with the absolute infinite, what Cantor himself wanted to call the absolute infinite. And it's a real question what kind of grasp we have of that. And for Cantor himself, it was a real question what kind of grasp we have of that. This ties in again with his religious convictions. He, at one point, said something like, I can't remember exactly how the quotation went, and in any case, I'm relying on an English translation, but something like the absolute can only be acknowledged, it can never be known. And this is a way of admitting that there's a grasp of the absolute that we lack. And so, as I say, my own view, for what it's worth, is that we have to think very seriously about whether we have any grasp on the truly infinite. And indeed, Cantor's work, so far from putting pressure on that skepticism, fuels that skepticism.
There's almost like a progressive breakdown of our sort of capabilities of understanding. It's at some point language, or everyday language, loses its grip on the infinite, but maths at least holds onto it and is able to give us a formal description of this ascending hierarchy of infinitudes. But then you reach, like you say, the sort of limit of that is something that Cantor admitted even maths can't grasp, and we're all at sea. The quote that comes to my mind actually is from Niels Bohr, who was, as you know, a physicist but also a bit of a mystic, and he said it was of atoms, where he said language. We must be clear that when it comes to atoms, we can only use language as poetry, and he meant, well, we at least have a mathematical description of how stuff moves, but we can't put it into everyday language. But in this case, there's some point where even the maths breaks down.
I think that's right. I mean, again, you've always got to be careful, as always in philosophy or maths or any other discipline for that matter. You've got to be careful to be as clear as possible and to define your terms as carefully as possible. And of course, there are ways of defining the infinite whereby it's just undeniable that Cantor showed that we can do the mathematics of the infinite. So, for example, if you define the infinite in the way that most mathematicians do, which is to say, if you call a set infinite when it is the same size as one of its own proper subsets, so like, the fact that the natural numbers is the same size as the set of even numbers, if you say, well, if that happens, if a set has that feature, then that's what it is for the set to be infinite. Well, fair enough. Okay, so if that's what you mean by the infinite, then Cantor has shown us how to do the formal mathematics of the infinite. He's dealing with sets that are like that. And if that's what you mean by the infinite, then he's dealing with infinite sets. But as I say, I mean, if you look up infinite in a dictionary, you're not going to find talk about uh, sets having as many members as one of their own proper subsets, or at least it would be a very unusual dictionary that would proffer that as any kind of definition. What you're going to find in the case of most dictionaries are words like endless or immeasurable or unlimited. These are going to be the terms in which the infinite is defined, or these are going to be suggested synonyms for the infinite. And then it's a real question whether they apply to the natural numbers or not. And so this goes back to the point that you were making, that what Cantor's work shows that that conception of the infinite, which arguably is the familiar everyday conception of the infinite, or one of the familiar everyday conceptions of the infinite, at least one of them, that conception of the infinite seems to resist mathematical treatment.
Does it create problems though for other conceptions of the infinite? For example, if we think of, perhaps we get some evidence that the universe is infinitely large, and there's some cosmological models which probably less fashionable now that suggest that it is, and there's even kind of wilder thought experiments from Max Tegmark where he believes we live in a kind of a type of multiverse where it's not just the laws of quantum mechanics which are producing branching, but actually all of the physical constants and possibilities are realized. Leaving aside perhaps Tegmark's vision, but if we just think about like a cosmologically infinite universe, that seems much more palatable than the sort of absolute infinite that Cantor was getting about. And it strikes me that as long as we don't allow for sort of infinite recombinations of the subsets, and or try to discuss infinite recombinations of the subsets of that infinite space, we'll have something which we can perhaps get something of a grasp on. Of course, it will be immeasurable and impossible for us to survey in its entirety, but it doesn't seem as paradoxical.
Yeah, no, that's I mean, I think that's an excellent point that you're making, and once again, I have to defer to you. You're the person with training in physics, and I'm not, and you know far more about this sort of thing than I do. But what about the idea that the infinite has application to physical reality? And you've sketched some of the ways in which that might be true, and certainly, I mean, if you go back to to Newton, if you go back to the 17th century, before people were aware of all the complications of relativity and all of that, it was taken for granted that space was infinite. Whether the physical universe inside space extended infinitely was a further question. I mean, Newton himself would have said that it did. He would have said that the physical universe was infinite as well as space. But the popular view was that space, at least, was infinite, and that time was infinite as well. That in both directions, that there was an infinite past and an infinite future. And 20th, 21st century developments in physics have shown us that it's not quite as straightforward as those guys thought. But nevertheless, there may still be room for the view that there's a kind of infinity exhibited in the physical world, and maybe there is still room for the view that space is infinite, even though it's no longer orthodoxy. And maybe there is room for the view that our universe is just one of an infinity of universes in a kind of pluriverse. So I think, we have to take these possibilities seriously, and I think you're quite right to raise the question, and then indeed to press the question and say, so what does this show us about what kind of grasp we have on the infinite? And it's a fair point, because this looks as if it is something close to a sort of everyday conception of the infinite. I mean, words like endlessness and unlimitedness and immeasurability do kick in at this point in a way that they don't with Cantor's mathematical work. And nevertheless, it looks as if we can make a kind of physical sense of what's going on. And I simply agree with all of that, and I think it's just a stark reminder of how unstraightforward all of this is, and how you have to think about the infinite in all its various applications and various manifestations. So, if the question, if the question arises, can we understand the infinite? Let's put it in those very bald terms. Or do we have a grasp of the infinite? The only legitimate answer to that question is it depends what you mean.
Mm-hmm.
Which is the answer that philosophers are always giving to questions, I know. But, you've just got to be more precise. And there are going to be some ways of making it more precise whereby the answer is yes. And there are going to be some ways of making it more precise whereby the answer is no.
Yeah. Yeah. I think that's right. And it gives some comfort, at least, that even though, as you hinted earlier, physicists sort of shy away from infinities, and, there's places where they're a bit frustrated, like the center of black holes, where you have something that appears of infinite density, and that kind of gets dismissed as a singularity. And we can't say exactly what's going on there. But it also excites people as well a lot, because it's these kind of limits or edge cases that often are where you discover really interesting things. Physics is really fond of boundary conditions as well. I remember, if you have to figure out something as simple as, what is the velocity that you have to throw something off the Earth so it escapes the gravity? Well, the way you run that equation is you have to imagine that you're throwing it to infinity, because that's the only place that it truly escapes gravity. And actually, I guess Newton's argument for why the universe was infinite was related to that. I guess he thought that if it wasn't, everything would kind of collapse in on itself under gravity. Of course, we could have a problem even with a physically infinite universe if part of the physics required us to think in terms of everything being kind of rearrangeable, and it was based on that. So there we might end up with somewhere where our physics is pointing us towards or down the route of Cantor, towards something which we really would struggle to grasp. So I don't know whether I hope or fear that we might end up with that, but that would be a certainly interesting thing. But we're some steps away from. I mean, that's very speculative.
But it is a reminder, isn't it, of how in physical reality there are all sorts of different ways in which the infinite might manifest itself. I mean, a lot of physicists obviously believe that, in fact, I think this is the orthodox view, that everything began with a big bang, And there are quite a few physicists that think that it's all going to end with a big crunch, that eventually gravitational pull will bring everything back down together into this tiny, infinitely dense blob, or however it goes. And your first thought might be, well, that's a striking example of how it's all ultimately finite. Big bang, expansion, contraction, big crunch, end of story. But of course, who's to say that it doesn't then just repeat? The idea that it might be bang crunch, bang crunch, bang crunch, bang crunch, going on indefinitely.
And you have to contend with the what's going on when it's just banging and just crunching. Is there a point at which everything is concentrated in infinite density?
I mean that's right. I just use the phrase infinite blob and infinitely dense blob, or some such phrase, and even as I was saying it, realized that was already a hostage to fortune.
We're running low on time here. Unfortunately, we are quite finite beings, and
yes,
I'd invite you to I'd like you to give us your thoughts on that. How is it that we, as such limited blobs of matter, are able to, and motivated, I think, and fascinated by these ideas? Where does it come from?
Well, I do. I mean, I actually do believe that you have just posed the $64,000 question. I mean, I think that is the really crucial question in all of this. What is it about us, finite beings that we are, that fascinates us about these questions? And if we can't grasp the infinite, if there is ultimately a sense in which the infinite is beyond our grasp, what are we even doing saying that we can't grasp the infinite? I mean, isn't that already paradoxical? Isn't that us grasping this thing which is ungraspable? So I think this is taking us right to the heart of all of these questions, actually. And again, if I can do a bit of axe grinding, I mean, this is a view that I've tried to defend in a number of places. I really do think that part of what's going on here is that we're exercised by the infinite because we're self-conscious, and in particular, self-consciously finite. I mean, in a way, what's going on here is that we're aware of our own finitude and exercised by our own finitude, which takes all sorts of forms. I mean, there's the simple fact that each of us only occupies a finite amount of space and will only be around for a finite amount of time. But there's all sorts of other respects in which we're limited and finite. And the universe is full of things that are limited and finite. But what's distinctive about human beings is that they're self-consciously limited and finite. They're limited and finite, and they're aware of the fact that they're limited and finite. And I think that's part of our fascination with the infinite, because there is inevitably this sense of a contrast. You think, well, okay, we are limited. It seems clear that we're limited, but as opposed to what? And does the sheer fact that we have boundaries inevitably mean that we have to reckon with the possibility of that which doesn't have boundaries? Is everything finite and limited? Is there no such thing as the infinite? Or are we finite and limited as part of some great cosmic story that is unlimited in some way? And I think, you posed the question, where does our fascination with the infinite come from, given that we're finite? And I think that's just an excellent question. And I think in a way, it's a question which serves as its own answer. Our fascination with the infinite comes from the fact that we're finite. Let's go back to young children. Maybe your 7-year-old son. Why is he? Why has he noticed at such a young age that numbers go on forever? Well, first of all, we would have been introduced to numbers as a way of counting the stuff around him. No doubt one of the first things that he did with numbers was, I don't know, count bananas in the fruit bowl, or toys that he had round about him, or whatever. This is a way of engaging with his finite surrounds. But then quite quickly, he realizes, but it doesn't stop there, does it? And this is a kind of self-consciousness that's kicking in. That's not necessarily going to be how it finds expression, but I think it is a kind of self-consciousness that's kicking in. He's aware that he's been using finite numbers to deal with the finite surrounds that he can engage with as a finite being. And then he thinks, but it doesn't stop there. And that's a self-conscious thought, it seems to me. Mind you, I've never met your 7-year-old son apart from briefly a little earlier. So I may be attributing thought processes to him which I shouldn't. But if he's the least bit typical of 7-year-old children, then I think this is something like what's going on.
Yeah. I think, as you say, it's the idea of our own limits leads us to think, well, what if things were otherwise? It's quite an elliptical quotation, but there's a wonderful poem by Chen Chen. I think the title might be, or it certainly has the line, "When I grow up, I want to be a list of further possibilities." Which, yeah. As you say, if philosophers are people who never grow up, that list of possibilities never gets closed down.
Again, that's interesting. You're talking about further possibilities, because that ties in with something that you said earlier. I can't remember now exactly how you put it, but you said something like, isn't one of our first thoughts about the infinite the thought that the way things are arranged is just one of the ways in which they can be arranged. You didn't put it exactly like that, but something to that effect. Yes, and again, I think that's the same thing that's kicking in, because part of this self-consciousness that I keep going on about is self-conscious awareness that we are limited, we are finite, and the actual is just one of a range of possibilities. Here's how things are. Here, you and I are engaged in conversation, but we might not have been. The technology might have thwarted us at the beginning of this process, or things might have panned out differently, or your 7-year-old son might have come in having had a nasty accident that you just had to attend to, that took priority over any conversation with me. And, there are all these different ways in which things might have been, all these different ways in which the stuff in the universe might have been rearranged. And that's a sense of the infinite as well. The sense, again, that self-conscious sense that the finite limitations of how things actually are point to a broader, infinite range of ways in which they might be.
Yeah. I think, this is one of those conversations where we could go on and on.
We absolutely
are.
could. Finite time has thwarted us, hasn't it? We come to the end. Yeah.
Well, thank you so much, Adrian. This has been what a wonderful tour. We've covered a lot of distance. I want to say infinite ground. It's been lovely.
Well, thank you very much. It was a lovely excuse to talk about the infinite, which I'm always happy to do. So thanks very much for inviting me to take part in this conversation.